But I'd like to get back to this notion of Aristotle, that basically the soul is a pattern imposed on the physical world. The soul is spontaneously formed, self-improving computer virus in the sense it is running on Turing machines made from organic chemistry. And it's crucial to understand how these machines differ from the linear Turing machines that we're currently using to describe computation in GPUs. The computers that we're currently using are defined in such a way that every state has exactly one possible successor state. Members of the Wolfram Institute community are multivay-pilled. They understand that the multivay system, the non-distributed Turing machine, is an extremely important concept. And the non-distributed Turing machine is one in which the successor state is not so well defined that you have only one possible one, but you have a multitude. And so instead of going into one possible successor state, you go into multiple states at once, which means you have a branching state space. But these states do not interact in the absence of a mechanism that is making them interact. They just branch out. And so an interesting aspect of the non-distributed Turing machine is not that it itself is random. The normal mathematical definition of a non-distributed Turing machine assumes that you simply go into all the states, which means it's a deterministic description. But if you are being computed by it, you don't know which branch you'll end up in, which is the particular branch that you're in right now. You will be in all these branches, but the observer doesn't know whether they're in the branch where the photon is going to the right or the left slit, or in which the neurons have converged to this representation or that representation. And this means that in a multivay system, there is genuine ontological randomness from the perspective of what's being computed by it. So the non-distributed Turing machine is a way to introduce true randomness into a deterministic process, into a deterministic universe. So basically the foundational substrate layer of reality could be deterministic, and yet you will find yourself in an intrinsically non-deterministic universe in which the apparent determinism is the result of the need to build control structure. And a similar thing could be happening in our own brain. If you look at the individual neuron, it's not fully deterministic. Given the same internal state of the neuron in functional sense, in the same environmental state of the neuron is not so tightly implemented. There is only one possible outcome, but there is a lot of noise that is happening. So the neuron is going to go into a range of possible states. And since you want your brain to control things, so it needs to be deterministic, you introduce redundancy to solve this. You use a group of neurons to represent something. The group of neurons has roughly the same internal state and roughly the same receptive field, but it's going to be effectively in a superposition. So the group of neurons implements something like a Hilbert space that needs to collapse if there is going to be make a joint decision between the neurons, but you will not remember having been in a superpositional state because that would require the observation by additional neurons, which would again be having these superpositions and so on. And there is at some point no point in trying to implement this in a mere mushy mortal human brain. And this means that the limitations of the human brain might make it impossible for you that it's best described using quantum mechanical formalisms. Yet this doesn't mean that the brain is a quantum computer. It just means that it's a system that, while being implemented classically, has properties that we typically associate with multivay systems.